Good morning, everybody. Obviously today I'm going to talk about JavaScript and obviously about how to handle concurrent programming in JavaScript. My talk will have primarily 4 areas. The first area will be on the concepts of concurrency. Then I'll talk about certain primitives that you can use within your application to build up a concurrent architecture. Then I'll talk about certain things that you may face when you're trying to convert your application to a more concurrent architecture. And then finally, if there's time, I'll do some demos. So without further ado, we can start with the concepts that everybody should know before they attempt to write concurrent JavaScript. First of all, concurrency is not parallelism. Concurrency is an idea where multiple things can happen, but not necessarily at the same time. Even if you have only a single processing core, it's possible to have a concurrent program. It's just that your program won't really run multiple bits in parallel. On the other hand, parallelism is true. It's really the holy grail of what we're seeking, where multiple things can happen at the same time. So you can make progress on multiple areas of data processing, etc., at the same time. And that's what we're talking about here. When you look at parallelizing your code, you may see certain benefits. And within the context of programming for a web application, there are 2 main benefits. The first one is the reduction of jank. Jank is what you see when you try to scroll a page up and down, and it doesn't quite respond. That's basically called jank. And if you move certain bits and pieces from the document's main thread to a web worker, for example, you can achieve usually jank reduction. So that's obviously better for the user experience. The other thing is that if you have your application running on a multi-core system, usually according to Firefox, if you decide to try to be more anonymous, Firefox pretends that you have 2 cores. So most computers have 2 cores now, at least. And so if you have only a single thread, then you're not really utilizing it fully. Obviously, most of the time, this is not a problem. But if you want to do certain things faster, and somehow you can't do it on the server, then you can try and convert your application to a more concurrent structure to make it work faster, basically. Obviously, concurrency or parallelization in this situation isn't without its drawbacks. The first drawback is sometimes when you try to parallelize a problem, you get diminishing returns because certain problems have serial parts and need to be processed serially. And these parts are not amenable to parallelization. So the speed up isn't really infinite. There is a limit to how much you can speed up before you reach diminishing returns. On the other hand, if you have a particularly large data set, then slicing it up and dividing it to multiple workers and aggregating results may take quite a bit of time. And in certain cases, this overhead would even exceed the amount of time you would spend working on the problem itself. So that's also something to keep in mind. There's a mathematical representation of basically the same thing. Basically, it says that there are certain bits of the work that cannot be parallelized, and if you hit these, then the work cannot be parallelized any further. This is bottleneck, assuming that the problem doesn't grow. All right. So let's say you have a web application. What can you do? First of all, there are actually 2 ways of concurrency within a web application. It's either preemption. Basically, you can think of this when you approach it via the lenses of preemption versus event-driven concurrency. So if you only have a single thread, even if you don't use web workers, don't use frames, you have only one single context, you can still write concurrent code. For example, when you issue an HTTP request, it's actually handled concurrently. The results will be delivered to you later via a callback. You can use promises to handle this better. You can use set timeout. Tell the system, hey, call me later. Or you can use request animation frame, or if you're lucky, request idle frame. And all of these things can happen within a single context. But sometimes you got to use multiple contexts because that's really the difference between concurrency and parallelism. And when you have multiple contexts, this usually means that you've got a document, and the document has a web worker, or you've got a document, and the document has an iframe, or you've got 2 documents in 2 different windows, and so on. You can use something called the channel messaging API to do this. So usually what will happen is you will have a document. The document will have a main script. The main script will spawn the workers that it requires. the main script will decide what to do with these workers and what to do with the responses it gets from the workers. So this is an example. You have a document. The document has a worker. Another example will be you got a document. The document has a frame. So usually that's basically how you do it. The first time, the version 1 of your code will look like that. Now, I'll talk a little bit more about channel messaging. I mentioned channel messaging, and this is how you actually communicate between your document and a context hosted within your document. You use something called the channel messaging API, and this basically means post message. You can do it against a window, you can do it against a worker, and you can listen for the message event when the worker or the subcontext has something for you back. But you have to keep in mind, there are actually 2 arguments possible in post message. Usually people will say, oh, post message isn't efficient because it copies data, but that's actually not entirely true. There are 2 arguments. The second one is optional. First of all, you have the data, which is copied. It could even have a cyclical reference if you wanted to, but obviously you really don't want to. However, do not stash your data directly in there. Try and look at the transferables list, and if you have a particularly large data, like a blob or some kind of representation of an image, then put it in the transfers list. So in the transfers list, I believe it supports at least array buffers. In certain platforms, it actually also supports bitmaps, but not all platforms. So you have to be careful and test it before you do anything else. Anyway, another thing you want to consider is when you have a concurrent architecture, does it really mean that the architecture is a responsive one? And in certain cases, yes, certain cases, no. For example, if you have only one worker, and the worker is busy doing something, then the worker wouldn't respond to new messages until it's already done with what it's doing. So if your worker is busy doing something, and you want actually something else from it, you have to have a way to preemptively cancel the work, which probably means killing the worker. And when you kill the worker, all the state held within the worker will also go away. So if you have only one single worker, and you want to preemptively cancel what it's doing, then the worker will lose all the state. This is basically bad design. So a better design possibly would look like this, where you have something in the middle, and you hold all the state in one particular place, and you have the work being carried out on this state down in a different place, and so on and so on. And this also allows you to have granular restarts, basically. Obviously, if you have been working with Elixir or Erlang, you will remind yourself that very soon your application will look like a bad version of Erlang. So you have to be careful. But in the meantime, if you truly have a need to write concurrent JavaScript programs, then it's possibly still a very good paradigm to emulate. Right, now the third part, adopting concurrency. So before adopting concurrency, you have to, again, think first, is your problem actually amenable to parallelization, or is it not? And could the problem actually be solved elsewhere, and so on? These are the ideas you should have in your head before you start writing code, because concurrency code is usually more gnarly, at least in JavaScript. It's much harder to debug, much harder to maintain. And any code you put in your repository is there forever, basically. Anyhow, if you truly decide to write a concurrent program, then you should try and make life easier for yourself. For example, you don't really need to interact with workers directly. You can wrap workers in the promise and so on, and the control flow will be better managed this way. All right, so for the time remaining, I would like to show you a few demos, if that's fine. Okay, it works. Very good. All right, so the first thing I would like to show you is called sleep sort. And this is kind of a funny example, but I promise it will be worth your while. So the first example I'll show you is how a problem that takes a long time may look like if you just do it within a single loop. So for example, here's my sleep sort function. As you can see, I wrap it in a promise. So when I call sleep sort function, it vends a promise to me, so it's easier to manage. I first got the problem empty list, responses empty list. I said, generate as many random numbers as I needed. And here's a check completion function, which is called every single time something completes. I check whether I've got enough responses. If I have, then resolve a problem. So for each problem, I basically, look at the value of the thing in the problems list, and then sleep that long, and when done, push the thing into a responses list. So I shall show you how it runs basically with timeout. Assuming that it works, of course. So let's say sleep sort 10, then function x, console log x. Yeah, so as you can see, it vents something very quickly. And if I were to do like 20, yeah, it gives me a sorted list of values using sleep sort. This is basically what you do with just doing a loop. However, well, you may think, we're talking about concurrency here. There's a single thread here. It's not concurrent. So why? Why do we stop here? We can do something else. We can do it with web workers. So this is an adaptive version of the same sleep sort. But as you can see, I have introduced something called a spawn function. First, I define the body of the worker in a function. This is so I can grab the representation of the function source code and stash it into a blob. So this worker only receives one type of message called ping. And in ping, it does the same thing, you see? Set timeout, and then a post message. And it sends a pong back. Anyway, so I grab the function, I convert it to a body and convert it to an immediately evaluated function expression. This is so I don't have to, do something weird like, strip the function parentheses thing and the brackets thing out from the string. I can just reuse it directly. This is cleaner. There's no regex involved. And generate a blob directly, so I don't have to make another file. And then create an object URL for that blob. So I get a blob URL now, and then use that to make a worker. So in a spawn function, we're still in a spawn function, and before we do anything else, add an event listener, listen for pong, and do the same thing. And then revoke the object URL so we don't have garbage lying around. This is the same check completion thing, and how do you do it? You can just so now we have proper concurrency. Now we can start spawning the workers directly, and then for each worker that has spawned, post message immediately. Or we can spawn everything and then initialize later. But I'll just run it and show you. Yeah. So we're still in the old one now with workers. You can see in the sources thing, you get a bunch of object URLs, and each of them is being used by one worker. And now, for example, if I were to do sleep sort 10, I will have spawned 10 workers and have each of them sleep the right amount of time. But sleep sort is terrible. And why is it terrible? I'll demonstrate. So now I'm going to add it. I'm going to edit this in, let's say, 50. It starts taking a while, and you can see it started returning incorrect results. Like this item at index number 4, it's incorrect. Why? Because there's actually an underlying limit on how many web workers can run concurrently for any domain. In Firefox, for example, 512, unless you specify. In Chrome and Safari, some other limits apply. So each web worker doesn't necessarily correspond to one underlying OS thread. There is an intermediate layer involved. However, the idea of a web worker is if you want to, you spawn it. You just can't guarantee that if you send a message, then everybody will get it at the same time, though. Right, so that's the first example, sleep sort. Now, let's talk about paralyzation overhead. So if you look at the paralyzation overhead, again, I prepared two versions, one in a loop, one in workers. So now, I have written a function. It computes a Fibonacci sequence, and it computes it for a set number of iterations. So 1, 1, 2, 3, 5, 8, 13, 21, and so on. Yeah. So my work here is to compute it for 1 million iterations, but don't worry, this is actually quite fast in JavaScript. So I've done it in a loop first. The page loads and computes, and it responds, OK, it has taken about 1,000 milliseconds to do it. How about using workers? You can see the same spawn thing. Here it said, OK, I want 100 workers. Yeah, because in loop, I did it 100 times, yeah? So in this case, I just did it in 100 workers at the same time. So all this, boilerplate is the same, spawn, post message, and so on. So let me look at the workers version. Okay, it's taken like 3.5 times as long, actually it has taken 3,540 milliseconds. So this is just, a very simple example, but you can see the overhead of setting up something and aggregating the results sometimes can be extremely high and sometimes even worse than the actual work you're doing. Okay, the third case, this is probably going to kill my machine, but hopefully not. Okay, so I got an infinite loop. So I got a Fibonacci sequence, and I got a magical function with a continuation. This is called a wake function, and when the wake function is done, it passes the continuation function itself. So this basically, it doesn't only destroy the JavaScript, virtual machine, also, continuously occupies processing power. So this may kill the machine. But let's see what happens. Okay, so this page actually doesn't even load anymore because Safari has frozen completely. So no matter, I can kill Safari. But what do you do? So here you can see, if you have something that potentially is malicious, you can isolate it. You can isolate it in an iframe. Or you can do the same work in a web worker. But there are critical differences between an iframe-based solution and a web worker-based solution. Let's see if Safari responds again. Okay, so let's say, okay, I've got an iframe version. Does it load? No, it doesn't even load. The iframe, at least at this moment, the context executing stuff in an iframe is hosted in the same process as the process hosting the top-level document. So an iframe really doesn't offer that much isolation. There is a work stream going on in Chrome, auto-process iframe, but I don't think it has completed yet. Anyway, let's look at the web worker version. It's the same thing, but I put this thing in a web worker. So restart Safari once more. I have to, try and make it not load. So as you can see, I've got a field here. I can still type, and it responds to my typing. But how do you know the work is actually running? Because if I look at the inspector, you can see there's a bunch of GUT messages here. So this means that if you run something terrible in a web worker, it actually is indeed isolated. And you could then, you could call the close function on the worker to close it. If you're really thoroughly done with it, you hate it so much, you can still close it, even if it's doing some kind of infinite loop shit. So a web worker really isolates very well. Okay. Number 4, what isolation doesn't do for you, off-screen canvas. So this is a more involved example, but I will just show you what it is. It's a canvas, and on every single frame, it picks a random emoji and draws it into a canvas. All right, so it's in an iframe, yeah? If you type, it's fine, yeah? But let's do something different. Let's say I want to blur everything by 10. It's kind of blurry now, but you can see it started slowing down, and when I type in the field, it doesn't react anymore. So it's indeed using up resources on the main thread. So in browsers, some browsers have off-screen canvases, some browsers don't. But let's see, this browser has no such thing. If I were to put it in an iframe again, what happens then? So it kind of responds, but it doesn't respond very well. An iframe, as I said earlier, an iframe's content is still hosted within the top-level document process. And so the rendition still goes through that process at the moment. There is no direct composition to the screen. So you can't always use an iframe to isolate bits that that is kind of synchronous, but you want to run asynchronously. If the browser platform doesn't provide that primitive, there may be a very good reason why they're not doing that. Okay, so last thing is basically a testament as to how far we've gone. So I got something which is called a pressure test of browser engines. First, I'm going to start with Bayer. Each of these gray squares is an iframe. And I'm scrolling up and down while the document inserts one iframe at a time up to 1024. So as you can see, the response is very smooth. And if you look at the CPU gate here, it's kind of flat. So it's fine, yeah? But what if we change it a little bit? Let's say instead of a plain iframe, let me draw something which is a little bit trickier. I add a frame with an animation. Okay, let's see. It already kind of is very sluggish, you know. Safari did improve a lot in this release, but Chrome actually starts, you know, freezing out at about 20. And as you scroll up now, you can see the composition artifacts start showing up. So, well, if you want to use iframes, you know, go ahead and do it, but don't use over 10. If you use over 10, something's probably wrong, I would say. All right, so what have we learned? One, in sleep sort, the messages you send to web workers to other contexts are casually ordered and buffered. If a worker is busy and you send them more information, it will respond later. The messages do not get lost. But web workers are not threads. You can spawn many, many more workers than threads, and it wouldn't really cause an issue. In demo 2, paralyzation overhead, there is a mechanical cost to paralyzation. As you can recall, 3 times basically 2 times slower than the loop version. On the other hand, there's also a very drastic difference in the amount of code you have to maintain. In demo 3, we showed infinite loops running in iframe and versus running in a web worker. So iframes do not really isolate very well at the moment, but hopefully it will in the future. And also, if you truly have a paralyzed system, then you have, you know, more problems concurrently. So you probably want to think about a way to cancel unwanted work instead of, you know, letting the work play out. Because on the client, you cannot just ask the client to get an additional core. It's not possible. The number of cores is fixed. So if you have some work that you don't want, you have to try and cancel it. In demo 4, you can see certain things may look polyfillable, but you can't really polyfill everything. Sometimes it affects the document anyway. And then sometimes it's very tricky. So you have to spend a lot of time, you know, debugging these things. In the final demo, well, if you really need to use iframes, don't draw anything. Even drawing a single spinner could cause a lot of rendition problems and composition problems as well. Anyway, that's all. Thank you very much.